Hi. So now let's take some practical examples and try to solve for what is alpha error, beta error, and power of a test. So let's start with the main hypothesis test. Suppose that a sample of n specimens is tested and the burning rate is observed, which we call x bar, which is the mean for that sample. And let's say we state our hypothesis as follows. Just like we did before, the h naught is mu equals 50 centimeters per second, which we call the null hypothesis. And h1 is mu is not equal to 50 centimeters per second, which is our alternative hypothesis. So what this really means is a value of the specimen that falls close to 50 centimeters per second, it does not conflict with the null hypothesis, which means if a value falls fairly close to the number 50, then we are okay, which means we can fail to reject or accept the null hypothesis. But if a value is considerably different or very much different or statistically significantly different, then there is evidence to accept or reject the null hypothesis. So typically, we always say you fail to reject or you reject. Accept is not used as often, but it is okay to at least understand, the basics of hypothesis testing. So if this value is considerably different, if you are collecting a sample and you're trying to find, the x bar, and it happens to be considerably different, then it means that it is showing evidence to accept the alternative hypothesis that your mu is in fact different from the value of 50 centimeters per second. So let's look at what are called acceptance regions and rejections regions. So this is our standard normal distribution, because we are assuming that we are looking at a normal population. So that hasn't changed. And our mu, we are assuming that it is 50. That's our null hypothesis. And let's say we have designated that if our mu, or if our x bar, lies between 48.5 and 51.5, that we will accept the null hypothesis, otherwise we will reject it. So which means that anything beyond 51.5 will be what is known as the critical region, or this is where if your x bar falls here, you're going to reject the null hypothesis, or if it is less than 48.5, you also reject. So this is called you reject and you reject. So this is called the rejection region. It's also called the critical region. And these values, or the limits of your critical region, are called the critical values. So 48.5 and 51.5 are the critical values, and the area that lies between 48.5 and 51.5 is what is called the acceptance region. So if it falls within this region, you are accepting the null hypothesis, or you fail to reject the null hypothesis. So this is diagrammatically representing what you're really doing with a hypothesis test. So once again, if your x bar happens to fall in this region, you're rejecting. Beyond this, you're rejecting. In between here, oops, in between in this value, you are accepting the null hypothesis or failing to reject the null hypothesis. So let's look at what is known as a type 1 error, or the alpha error. So alpha error is nothing but the rejection of h naught when it is in fact true. So alpha is the probability of a type 1 error, and you're rejecting h naught when it is true. So in the current example, think about what that really means. So alpha is you're trying to reject the null hypothesis when it is true, which means when will you reject something? You will reject when your x bar is less than 48.5, or your x bar is greater than 51.5, but when your true mu is given to be 50. So that is when you will create what is known as a type 1 error, and this is how we compute it. So alpha is nothing but, and once again we can standardize this expression. So x bar minus mu divided by sigma over root n. Remember from the previous module, from the previous chapter of confidence interval testing. So this is how you would standardize the normal distribution. So x bar minus mu sigma over root n is less than 48.5 minus mu divided by sigma over root n, square root of n. Let's say it's been given to us that your mu is 50 and standard deviation is sigma over root n. Let's say the standard deviation is or sigma is given to be 2.5, and let's say we have 10 samples, and we can compute that to be 0.79, the sigma over square root of n. So the way we compute this is alpha is probability, so this is nothing but z, so that's why I can replace that by z. Probability that z is less than 48.5 minus 50 divided by 0.79 plus probability that z is greater than 51.5 minus 50, where mu is 50, divided by 0.79. So when you simplify this, it turns out to be this z being less than negative 1.89 and 1 minus probability that z is less than positive 1.89, and this happens to be alpha equals 0.059. So all this really means is that 5.9% of all random samples would lead to the rejection of H naught when it is true. So which means that when you're randomly sampling, given this acceptance region that you have chosen, the acceptance region that you have chosen is 58.5 and 48.5 and 51.5. Given that this is your acceptance region, 5.9% of all random samples will lead to the rejection of H naught when it is true. So this error will be committed 5.9% of the time. Now take a few minutes to go back and look at the type 1 error and make sure you have understood that concept, because it is very very critical that you understand that clearly. You can pause the video, go back, you have the notes on D2L, and there are some sample problems posted. So why don't you try to solve a couple of those to make sure you understand the type 1 error calculations. Now let's move on to type 2 error. Type 2 error is when you are failing to reject the H naught when it is false. So which means you are accepting the H naught when it is false. So for this calculation we obviously need an alternative hypothesis or a specific value. So we need a specific value for the alternative hypothesis. Suppose that it is critical and important to reject the null hypothesis when mu happens to be 52 or when mu happens to be 48. And how do we compute that value? So we're trying to find the beta. Beta is probability that x bar lies between 48.5 and 51.5 when in fact mu is equal to 52. So you're really looking at the acceptance region, so that will be the beta. But here your mu is no longer 50, your mu becomes 52, or in another case you can test for mu equal to 48, but it would be the same value. So beta error happens when we are accepting H naught even when it is false. So we need a value to test it. So we can find it as the probability that x bar lies between 48.5 and 51.5 when mu is 52. Bear in mind the mu was 50 earlier, but here we are saying that let's say the true mu happened to be 52. So how would you compute the beta error, where you are actually accepting something when it is actually false, which means your mu was never 50 to begin with, it happens to be 52. So how would you compute these values? So beta, once again, will be the probability that x bar lies between 48.5 and 51.5 when the mu is 52. So I can compute this as the probability that x bar is less than 51.5 minus the probability that x bar is less than 48.5. And if you standardize these expressions, and this 0.79 has not changed, but remember, look at what has changed here. This is 52 and not 50 anymore. It was 50 previously in the alpha error case, but in the beta error we are just considering, we're throwing that value in there, 52 or 48. We're saying that what if it happened to be 52, then we do these calculations. You can repeat these same calculations with mu being 48. So this happens to be, beta is 0.2643. So by symmetry, if you take 48 also, you would get the same value. So what this really means is that there is a 26.43% chance of failing to reject H naught when it is false. So which means that there is a 26% chance, approximately, let's say 27% chance of accepting. So given your region and given this true mu of 52, there is a 27% chance of actually accepting the H naught when it is in fact false. So bear in mind that the beta, or the beta error, the type 2 error, increases as the true value of mu becomes closer and closer to the hypothesized value. So this beta error is going to increase, and think about why this is possible. Pause the video and think critically about why beta would increase as the true value of mu becomes closer and closer to the hypothesized value. So how about, maybe you can take a break and actually compute it with 50.5 and see if beta has increased or not. Okay, so instead of mu being 52, compute this value with mu equals 50.5 and check if beta has increased, and you will see that it will. So that will be the beta error. So what about the power of a test? So the power of a test is nothing but the probability of correctly rejecting the null hypothesis when the alternative is true. So clearly you want this power to be as high as possible, right? Because this is really the sensitivity of your test, and you want this to be, your test to be very sensitive to identify the fact that you want to reject the null hypothesis when the alternative is true, which means you want the test to be powerful. So if beta is accepting null hypothesis when the alternative is true, 1 minus beta will tell you the probability of rejecting the null hypothesis when the alternative is true. So for the previous example, or for the foregoing example, the example that we've been looking at throughout this section, your power of test is 1 minus beta, or beta as we computed earlier was 0.2643, or the power of the test in this case is 0.7357. So power, like I've been talking about, is a measure of sensitivity of a statistical test. So if the true mean is 52, our test will detect this difference 73.57% of the time. Okay, let me state that again. If the true mean is 52, our test, the test that we have designed, will detect this difference 73.57% of the time. So higher the power, the better. So you want to design tests with maximum power. Okay, so you want this 1 minus beta value to be as high as possible. So that is called the power of a test, and we'll talk about the Neyman-Pearson lemma like I talked about, which will tell you how to develop the most powerful test when you're testing the hypothesis. So once again, let's just quickly summarize. So in this thing, we talked about the alpha, the rejection rate, the rejection region, the acceptance region, the critical values. Then we went on to talk about the type 1 error, or rejecting the H naught when it is in fact true. And if you have selected an acceptance region, anything that falls beyond that would be, that's how you would compute it, where x bar being less than 48.5 or x bar being greater than 51.5, and the true mu is 50. So that will be your probability of rejecting the H naught when it is true. And then we went to the type 2 error, which is failing to reject the H naught when it is false, or accepting the H naught when it is false. So for this we really need a new true mu, not the one that we hypothesized with. We need a new mu value. So if we are saying that it is actually 52, then we can compute probability that x bar is between 48.5 and 51.5 when mu is 52, or you can choose another value of 48 or 50.5 and check what is happening to the beta error. And we said that the beta increases as the true value of the mu reaches the hypothesized value, and you can test that. And after this video I want you to take a few minutes and actually calculate this value for 50.5, or pick another value, pick 51, and test the fact that beta increases as the true value of mu approaches the hypothesized value of 50. And then we went to the power of a test. So power of a test is nothing but 1 minus beta, and it is really the sensitivity of your test, and it is telling you how your test performs in detecting a true alternative hypothesis. So that so this should conclude this part of the module. And what we'll do is we'll next go to what is called a p-value test, and then we will develop the 7-step procedure for hypothesis testing, and then we will solve a few problems both by hand and using Excel, and then we will move on to the next module where you'll talk about testing for hypothesis when variance is also unknown.